Hi guys, I'd like to talk a little bit about dimensional analysis and unit conversion today. This is a strategy that we use to convert from one type of unit to another. The dimensional analysis method is also called the factor label method. I prefer dimensional analysis because I think it sounds more like we're traveling through space and time, but you'll see factor label method in some places. So I have here that it's a handy and elegant way to convert units, and I just think that it's one of those nice things. It's a tool that you can really utilize in a lot of different areas of life. I've had students come back and tell me that they used the factor label or the dimensional analysis method when they're cooking or in business classes, and so this is just one of those skills that'll translate to a lot of different areas. And it's as easy as multiplying by 1 because we're looking at different ratios and using those ratios then to go from the units that were given to a unit that we're looking for. So in this video, I want to focus a little bit on metric to metric because as scientists, we're utilizing the metric system. So we might have a problem that looks like this. So hopefully you're pretty snappy with your metric prefixes. So centi, of course, gives you an informational piece about how many of these smaller units are in the larger base unit of a meter. And we want to know how many centimeters are in a kilometer. So when I'm doing metric to metric problems, because of the way that the metric system is set up with a base unit and then units that are larger and units that are smaller, I like to do everything with reference to the base unit. So we need to figure out what we know. If we're given a problem like this, what information do we know that's going to get from one unit type to another? I'm given kilometers, that's a big unit, and I want to know how many centimeters are in there, which is a smaller unit. So the first thing I need to know is that 1 kilometer is equal to 10 to the 3rd meters, or 1,000 meters. And another important piece of information that I need to know is that in 1 meter, in the base unit, there are 100 centimeters. And centi, like 100 cents in a dollar. That's the way that I always remember that. So if I know these relationships, then that's going to give me a ratio that I can use as a multiplying factor to go from one unit type to another. So the way that we would set this up is by starting with the value that we're given. And again, we as scientists care about values. That would be a number and its units. And my first ratio that I'm going to set up here needs to divide out the units that I started with on the top. So I need to have kilometers on the bottom. And it's trying to get to a unit that I have information about. Now I may, if I happen to know the relationship between kilometers and centimeters, I could go directly from one to another. So if you know that relationship off the top of your head, great, you could just do this in 1 step. I'm going to show you how to do it in 2 steps by using this base unit as kind of a go-between. So I'm going to put meters on the top of mine because meters are in common between the information that I have and the information that I'm looking for. So I personally like to set up each of my ratios first, where the units are going to divide on the bottom with whatever I have here. So the units are going to divide on the bottom with what I have on the numerator here in this factor. And so if I'm going from kilometers to meters here, then I go from meters to centimeters here. So I'm given kilometers. They'll divide out here. I got to meters using this ratio. They'll divide out here. I'll be left with an answer in centimeters. Now, once I have my units kind of mapped out, then I can put in the relationships because each of these unit converters is a ratio that essentially equals 1. So this unit conversion factor, that's what we call this, a conversion factor, is a ratio, and that ratio is equal to 1, which just means that it's an equality. Whatever it is that's on the top has to be equal to whatever is on the bottom, and that's how it equals 1. So in 1 kilometer, I have 1,000 meters. And same with this one. This is also a conversion factor. That means that this ratio has to be equal to 1. So in 1 meter, I have 100 centimeters. And again, we're scientists, so we think about this in terms of scientific notation. Now, my kilometers divide out, my meters divide out. I'm left with an answer in centimeters. What I'm functionally doing here is multiplying by 2 ones, which will give me some sort of equality in units that are going to give me the units that I'm looking for with relation to the units that I'm given. And that's just kind of the name of the game here. So when we multiply this through, remember when you're multiplying scientific notation, you add the exponents. So this would give you 3.52 times 10 to the 5th, and then centimeters. Now, at the end of any mathematical problem, so if I was to plug this into my calculator, and this is the answer that my calculator gives to me, then I am very untrusting of my calculator. I don't know about you, but my calculator has lied to me in the past. And so in order to avoid calculators lying to you, there's kind of 2 things. We need to check our answer. And the first thing that we check then is the magnitude of the answer. Does it make sense, right? Are we expecting this number to be greater than the number I started with or smaller than the number I started with? I think that's an important first question, because if I get a number that is vastly larger or vastly smaller than my initial value, and I wasn't expecting it to be that way, then there might be an error along the way. So let's think about this check for this particular problem. I started with kilometers, which is a large unit, right? If I was thinking about the distance from Ellensburg to Moses Lake, then that would be in kilometers. So I have 3.52 kilometers, and I'm going to a unit that is something that we can picture on a meter stick. If it's divided into 100 pieces, then that is 1 centimeter. So I'm going into a unit that's very small. If I have a small unit that I'm looking for, and I start with a larger unit, I would expect this number's magnitude to be large. I would expect to have a greater number of centimeters than kilometers, and I do. So that's good. So check 1. The second thing that we check as scientists who are concerned with measurements and the precision of our measurements are sig figs. So I have a video on significant figures and kind of the rules and how we round. And so if we're thinking about sig figs with dimensional analysis, we're doing multiplication and division. And so we're going to factor in any of the inexact numbers, and that's going to help us to round our answer. So if I look at this number here, this is inexact. My first initial number, my 3.52, is an inexact number. The next 2 factors, this guy and this guy, that I used as conversion factors are both exact. There are 2 types of exact numbers. We said we can either have a count, so I went around and counted up the number of apples on the tree, and unless I'm the worst counter in the history of the world, then I don't have any sort of uncertainty of my error. That's just the number of apples there are. And in definitions then too, so the defining factor of a kilometer is that it's made up of 1,000 meters, then that's also exact. So it doesn't matter how many significant figures I have here. They're not going to factor into my rounding of the answer. So the only one that matters is this inexact number. So this guy has 1, 2, 3 sig figs. So my answer needs to have 1, 2, 3 sig figs. So we're good. Okay, so we're the right magnitude and we have the right number of sig figs. Okay. Now let's also, while we're here, talk about going from the English system into the metric system. Let's give myself some new paper here. So if you're given units in the system that we use here in the US, which is the US customary system, which if you've seen my other videos on that, you know how I feel about that. But given that these are the units that we know and that we use, then we need to be able to convert them into units that the rest of the world uses, like the metric system. So let's take a lizard. Let's say how many grams is my 5.5 pound lizard. So I have a lizard that's 5.5 pounds and I want to know how many grams there are. Well, it's not as easy to know which factors I have when I'm not in the metric system. The metric system is nice because it's base 10, so everything is 10 times greater or smaller. I just have to know my prefixes, and that tells me where I am relative to the base. So I have to look up some information for this. So if I look it up, then what I need is I need to figure out how many grams are in 1 pound. So I look that up on Google, or maybe I'm given that information by my instructor, who, if I'm your instructor, I will give you this information if it's in English to metric, because it's lookupable. Then let's round this up to 554 grams. So I think it's 453.6 grams is 1 pound, but let's call this 454 for our purposes. So let's take our method, dimensional analysis, and we're going to start with pounds, and I want to multiply it by something that has an equality, which means that the numerator and the denominator have the same value. They just have different units, and I need to have pounds on the bottom, and I want to find out how many grams there are, so that needs to be on the top in my numerator. And now if I was to multiply by this unit conversion factor, then that would divide out my pounds and will give me an answer in grams, which would answer the question, how many grams are there in my 5.5 pound lizard? So now I plug in the relationship. So for every 1 pound, there are 454 grams. And so this relationship then functionally equals 1. When I multiply this 1 times my initial starting quantity, then the units will divide out, and I end up with 2,497 grams. Now we need to check. We need to check our answer, because answers in science have physical meaning. And if we have a physical meaning to our answer, then the value, the number and its units become that much more important. We need to make sure that we're reporting a thing that physically makes sense. So let's check. The first thing that we want to check is it going to be bigger than the starting number or smaller? So kind of bigger or smaller. Now, if we look at this relationship, there's a lot more grams in a pound than pounds in a gram. So if I have a few pounds, then I'm going to have a lot of grams, right? So I would expect my answer to be larger than my starting quantity, and it is, so that's good. Now the second thing I need to check for is sig figs. I need to look to the significant figures. This was a relationship, so this is an exact number. This is a definition that you were given, so it's exact. We don't have to factor it in when we are rounding our answer. So I'm going to be limited then by my inexact number, which in this case is the mass that I measured, or the weight that I measured. So I took my lizard, I stuck him on a scale. He was 5.5 pounds, and 5.5 was the value that I got from my measuring device. So based on my precision, I'm going to have 2 significant figures. But this does not have 2 significant figures, so I need to round this thing to 2 sig figs. That means that this one and this one, right, counting over from the left, 1, 2 are significant, which means I'm looking to this one to round. That word is round. It doesn't look like round, but that's what it is. So we know that we're going to round up. In this case, it's greater than 5. So 1, 2 significant figures, grams. Now we said before that zeros are a little bit ambiguous, so if you want to make this less ambiguous, then it's better to write it in scientific notation. When in doubt, scientific notation is the way to go. And that would give you an answer using dimensional analysis with 2 significant figures.